Okay, so get ready for this one because we're diving deep into the search for a theory of everything. And honestly, the title alone just grabs you.
It's definitely a heady concept.
You sent in some really interesting excerpts from this RT documentary, Finden wir die Weltformel.
Yeah.
Imagine, like, just one equation to explain the entire universe.
It is a pretty profound human desire to want to find order in all the chaos, to find like these fundamental laws that govern everything around us. It's a pursuit that's really captivated thinkers for centuries.
Yeah, and for a while there, it really did seem like classical physics was kind of pointing us in the right direction, right?
Yeah.
Newton's laws of motion, gravity. It felt like we were putting together this predictable clockwork universe.
It's really interesting how that whole idea of predictability has really shaped the way we understand the world.
Right.
Well, Place, with his idea of a demon, kind of took this to like the extreme, right? He was basically saying that if you knew where every single particle in the universe, where it was, you could theoretically predict the future with absolute certainty.
Yeah. A demon? That's quite an image.
Like a cosmic supercomputer.
Right.
Crunching all the numbers.
Okay, yeah. A cosmic supercomputer predicting the future. But then quantum mechanics kind of enters the scene and shakes things up, turns that neat, predictable world upside down.
Precisely. Quantum mechanics was a revolution, and it really turned everything on its head from those classical physics ideas. Because at that subatomic level, the universe was anything but neat and tidy.
Right.
Energy, for example. It isn't this smooth, continuous flow that, we might imagine. It's actually delivered in these little packets, what we call quanta.
Like a cosmic vending machine, where you've got to have the right amount to get what you to make a purse.
Exactly.
Yeah.
That's a great analogy. And then you have superposition. This is where things get really mind-boggling.
Right.
The idea that a particle can exist in multiple states at the same time until we observe it.
Yeah, the documentary mentioned like a coffee cup being in two places at once. I've lost my keys. I don't need a coffee cup being in two places. But so it's like the act of us observing something forces it to choose a reality. I mean, how does that even work?
It's one of the biggest brain twisters in all of quantum physics because it's not even that we just don't know where it is until we look. It's literally everywhere it could be.
Okay.
Until you look. And then all of a sudden it's like, oh, it's right here. And it's like the universe is waiting for you to decide where the cup should be, which is kind of a trippy thought.
Okay, so that my brain is melting a little bit at this point. So if these quantum rules govern these tiny particles, how do they affect the universe on a larger scale?
That's the million-dollar question. And to kind of unpack that, we need to talk about the four fundamental forces of the universe. And these forces really are like the cosmic blueprint, dictating how everything interacts, from the smallest atom to the largest galaxy.
Okay, so lay it on me. What are these fundamental forces? Gravity's got to be one of them, right?
You got it.
Okay.
Gravity, the force of attraction between objects with mass. That's why we're anchored to this planet.
Keeps us grounded.
It keeps us grounded, and it's why the Earth orbits the sun. And then we have electromagnetism, the force behind light, electricity, and magnetism.
Okay, so I'm starting to see the bigger picture here. So we've got gravity, electromagnetism. What about the other two forces? What roles do they play?
So we've got the strong nuclear force, which is like the ultimate glue. It binds protons and neutrons together within the nucleus of an atom. And without it, atoms would just simply disintegrate. And then lastly, we have the weak nuclear force, which governs radioactive decay.
Four fundamental forces. Sounds almost simple when you put it like that.
It does.
But I'm sensing that it's not that simple because I'm guessing the real challenge is how you actually unify all of these forces. So how do we reconcile these cosmic forces when some of them seem to be playing by different rules?
You're spot on. It's not simple in the slightest, actually. Unifying these forces has been one of the biggest puzzles in physics for over a century, because three of them, electromagnetism, the strong force, and the weak force, are beautifully described by this wacky world of quantum mechanics.
Right.
But gravity dances to a different tune,
Okay.
this more elegant rhythm of Einstein's general relativity.
So we've got these two incredibly successful theories, quantum mechanics, general relativity, but it sounds like they just don't agree when it comes to gravity.
Precisely. Trying to fit a square peg in a round hole. And bridging that gap has been this ultimate goal for physicists who are striving for this unified theory. The documentary even mentions some of the biggest names in physics who've devoted their lives to this cosmic puzzle. Einstein, for example. He actually dedicated much of his later years to this quest after he came up with this groundbreaking theory of general relativity.
Einstein, known for his genius, even he struggled with this.
He did.
What was it specifically that stumped him, though, in his search for a unified theory?
So Einstein desperately wanted to unify gravity and electromagnetism. He had this vision of the universe being governed by these elegant, unified laws, but the deeper he delved into that quantum world, the more elusive that unification seemed.
Interesting. So even Einstein had these scientific struggles. Now, the documentary also mentions Stephen Hawking. So what role did he play in this search for a theory of everything?
So Hawking was another titan in the physics world, obviously.
Yeah.
And he made some monumental contributions to our understanding of black holes of the early universe. But he, like Einstein, was driven by this pursuit of a unified theory.
Were there any specific challenges that he faced in his research? Because it's not like this was just a matter of missing a few puzzle pieces, right?
No, not at all. One of Hawking's most important discoveries actually presented a major obstacle in this quest for a theory of everything. His work on black holes, especially his discovery of Hawking radiation, really emphasized this conflict between general relativity and quantum mechanics. So it just goes to show how complex and challenging unifying these two pillars of modern physics really was.
So even the brightest minds hit roadblocks on this road to unification. But it hasn't been all dead ends, right? Because, I mean, we have successfully unified some of these forces before, haven't we?
Yeah, that's an important point. History shows us that unification is possible.
Okay.
Take electricity and magnetism, for instance.
Right.
They were once considered these separate phenomena, but thanks to the brilliant minds of physicists like Faraday and Maxwell, we now understand them as being two sides of the same coin, electromagnetism. And that unification was a major, major triumph in the physics world. And then there's the electroweak theory, which combines the electromagnetic and weak forces.
Wait, hold on. You're going to mention a theory with a really cool name like electroweak and not explain it. I need to hear more about this. So how did this unification come about?
Okay. So imagine the universe as this giant cooling soup after the Big Bang.
Oh, okay.
Right? So at extremely high energies, like those present shortly after the Big Bang, the electromagnetic and weak forces were actually a single unified force. But as the universe cooled, this force split into the two forces that we observe today.
Oh, wow.
And the electroweak theory beautifully describes this split and the conditions under which these forces act as one. So it's a perfect example of how these seemingly different forces can be unified under the right conditions.
So there's hope yet.
There is.
The electroweak theory shows that this kind of unification is achievable even if it happened under these crazy extreme conditions.
There you go.
Now, this documentary also delves into some pretty wild, mind-bending theories. Things like string theory with its tiny vibrating strings composing the universe, and loop quantum gravity, which suggests that space itself is made up of these tiny, indivisible pieces. I mean, these sound like concepts straight out of science fiction.
Yeah, and that's part of what makes this whole quest so captivating, because these theories are really pushing the very boundaries of our imagination. String theory in particular offers this incredibly elegant way to bring gravity into the quantum fold.
Okay.
But it comes with a really mind-blowing caveat.
Okay, I gotta ask, what's the catch with string theory?
So it predicts not just one universe, but potentially an infinite number of universes, what we would call a multiverse.
A multiverse. Okay, now that's a lot to process, even for me. So why does string theory need a multiverse to work? I mean, how does that even make sense?
It's a consequence of the theory itself. So string theory, it replaces these point-like particles, which we normally think of, with these one-dimensional vibrating strings. And these strings, they vibrate at different frequencies. Each frequency corresponds to a different particle.
Okay, I'm following so far.
Okay, but here's the kicker. These vibrations don't just exist in the three spatial dimensions that we experience.
Okay.
String theory actually requires extra spatial dimensions, curled up way too small for us to ever see.
Extra dimensions. Vibrating strings. This is a lot to wrap my head around.
It is, and here's where it gets even more wild. The way that these extra dimensions are compactified determines the laws of physics in our universe.
Oh, wow.
But there are so many ways to compactify these extra dimensions, each potentially leading to a different set of physical laws, and hence the multiverse.
So string theory suggests that our universe is just one of countless others, each with its own unique set of physical laws. That is a lot to unpack. Okay, what about loop quantum gravity? What's the core idea behind that theory?
So loop quantum gravity takes a different but equally radical approach. Instead of adding all these extra dimensions, it suggests that space itself is not actually smooth and continuous, but it's actually made up of these incredibly tiny, indivisible chunks, sort of like pixels on a computer screen,
Okay.
but on a scale far, far smaller than anything we can currently observe.
Wow. So instead of trying to force gravity to play by these quantum rules, loop quantum gravity suggests that space-time itself is already inherently quantum,
Yeah,
built from the ground up with these fundamental building blocks. That's a pretty wild concept.
it is. And if it's true, it would mean that gravity just naturally emerges from these quantum properties of space-time itself.
Both of these theories, they sound mind-bogglingly complex. How do you even begin to prove any of this? I mean, what kind of experiments could you possibly run to test these ideas, especially when they're dealing with these realms that are so far beyond our everyday experience?
Well, that's the billion-dollar question, isn't it?
Yeah.
The documentary highlighted some of the crazy challenges that physicists are facing.
Yeah.
Because to really test these theories, ideally, we need to be able to recreate those extreme high-energy conditions present in the very early universe.
Yeah.
Like fractions of a second after the Big Bang.
Yeah, like sounds like somebody needs a much bigger particle accelerator.
Right.
But seriously, how do you even begin to recreate the Big Bang in a lab?
Yeah, it's a monumental task,
Yeah.
to say the least. But,
Yeah.
that doesn't mean physicists are just giving up.
Right.
There's some really ingenious experiments underway, really pushing the boundaries of what's technologically possible.
Yeah.
The documentary mentioned one in Geneva that's actually attempting to measure the gravitational field of these incredibly tiny objects, hoping to detect any quantum effects.
Wait, hold on. They can measure the gravity of something so small that it makes a grain of sand look gigantic.
I know.
How is that even possible?
That was my reaction, too. They were talking about measuring the gravitational pull of this tiny gold sphere.
Okay.
And get this. Its gravity is 10 million times weaker than a snowflake.
Wow.
The level of precision involved is just mind-boggling.
Okay, that officially blew my mind.
Yeah.
So let's say, hypothetically, we could actually prove these theories. What then? What are the implications of us actually finding a theory of everything? Would it be the ultimate answer, or would it just be the start of a whole bunch of new questions?
Well, that's a question that sparks endless debate among physicists.
I bet.
Because some people believe that finding this theory of everything would be like the end of physics in a sense. Like we'd finally have this beautiful, complete picture of the universe and how it all works, a cosmic Rosetta Stone.
Right.
But others think that it's just as likely, if not more likely, that it would just open up a whole new can of cosmic worms. Like the more we know, the more we realize what we don't know, right?
Right, yeah.
So finding the theory of everything, it might not actually answer all our questions.
Right.
It could very well lead to even deeper, more profound ones. Just imagine the mysteries that might unfold once we actually have a glimpse of that universe's underlying code.
Yeah, it's exhilarating and kind of terrifying to think about all at the same time, right?
Yeah, absolutely.
It's like finally reaching the summit of a mountain that you've been climbing your whole life,
Yeah.
only to realize that it's surrounded by a much larger, completely uncharted mountain range.
A perfect analogy.
Yeah.
And then, of course, we have the philosophical implications to think about. Like, if everything is, at its core, governed by this single deterministic equation,
Right.
what does that mean for things like free will?
Whoa, see, now that's getting really deep.
Right.
Yeah.
It's like a cosmic upgrade to that whole Laplace's demon idea.
Right.
Except now, it's not just some hypothetical being, it's the universe itself, potentially playing out this predetermined script.
Wow.
It really makes you think.
It really does, yeah.
But, even if we never actually find this elusive theory of everything,
Yeah.
the pursuit of it, I think, is invaluable. Every experiment, every theory, even every dead end, it brings us a little bit closer to understanding the universe and our place in it.
That's a really good point. It's like we're on this incredible cosmic adventure, and even if we never reach that final destination, the discoveries that we make along the way, the sheer awe of exploring the unknown, that's what really matters.
Exactly. Each step we take, each theory we explore, it just expands our understanding of the universe and our place within it. And that, in and of itself, is incredibly profound.
That's a really beautiful way to look at it. It's not about reaching the finish line. It's about the thrill of the chase.
Exactly.
That constant exploration, the discovery.
Precisely.
It's almost like it's built into us, this need to search, to uncover these secrets.
Yeah, it's that burning curiosity that really makes us human, right? Try and understand not just what we see, but why it's there in the first place. And you never know.
Yeah.
Maybe the real beauty isn't about finding all the answers.
Yeah.
Maybe it's about the journey itself, the pursuit of knowledge, whether we ever truly get to that final destination or not.
That's a really beautiful way to look at it. It's not about the finish line. It's about the thrill of the chase, that constant exploration and discovery.
Exactly. And each theory we explore, each step we take, it just broadens our understanding of the universe, our place in it. And honestly, that in itself is something truly amazing, don't you think?
Absolutely. And to our listener, as we start to wrap up this incredible deep dive into the search for that theory of everything, we'll leave you with this question to ponder. What is it about the universe's mysteries that just seems to resonate so deeply within us? Is it the beauty of a unified theory that we crave? Or is it that endless pursuit of knowledge that really truly captivates the human spirit?